Hello, everyone, and welcome to another session of Your Desk University, bringing you live learning with AEC tech experts directly to your desk. It's been an honor bringing this series. We're at 18. This is our 18th session now. And today we're going to be talking about data trees. For those of us who are using Grasshopper, we might really love Simplify and Flatten, but get ready to get those just thrown completely out the door, as our speaker, who's the developer of Heumann UI, Andrew Heumann, kind of shares a little bit more about data trees and how to really keep consistent data throughout your model so you can get the most out of it. And if you want to ask him why he suggests that, that's a great question to keep for him. Other sessions that we have had, I want to kind of just mention a couple other sessions we've had on Grasshopper. We had Repeatable Grasshopper from Kadim Al-Asadi, and that's on our channel. He talked about how to use clusters and use stadiums and fine cabinetry as his two examples for creating your own clusters and user objects. That's a massive array of projects right there that can be included in that. And then just last, I think Tuesday, we had Rhino Inside with Dane Stokes from ZGF. And he talked about Rhino Inside, a little bit how to use it. And then his focus was on visuals for management. So how can you look at your Revit model using this new platform and create animations and graphics that go along with that. Also, these can all be found on our website right here under past recordings. If you do go to the bottom of our website, I'm going to go to upcoming talks here. At the very bottom, you'll find join us on Slack. And that's where you can have continued conversation with our speaker. And we would love to see and hear from you there. We have about 130 people so far that have joined, and we would love for you to join as well. Finishing up this series, we have two more sessions upcoming. One is Dynamo, things you may have missed along the way. And then next week on Tuesday, we're going to hear from an architect, a fabricator, a pragmatic idealist or researcher, and an engineer about the future of building envelopes. I'm personally really interested in seeing where they take this conversation, and make sure you sign up for those and join. And I think John will post the links for those in the chat right now. If you are joining us live, we really want to hear from you. And Andrew is watching the chat, and I will be, and I'll be feeding him the questions as we go. And now that I've introduced him like 3 times, why don't I just bring him onto the screen here? Andrew, how's it going? Nice to see you.
Hi everyone.
Andrew, I am like really excited to hear what you have for us. For those who don't know Andrew, in the past 10 years, he's worked at NBBJ, Woods Bagot, and WeWork, and now he's a software developer at Hypar, a company leading the edge in generative design. And I know that they're integrating things or doing generative design for mechanical systems, structures, room layout, all kinds of different things. Also, he's the developer of Heumann UI, which many of you already use in your Grasshopper, and I'm hoping that maybe we can either get a commitment or I can hook him into doing another session next semester on Heumann UI and all the possibilities there. If you haven't seen him posting them, he's been doing a training series also during, I don't know, Andrew, is it just during COVID or is it a new thing you're starting that you're going to continue doing?
I mean, it was sort of inspired by the whole quarantine thing, but I've really enjoyed it, so I'll probably keep it up, as long as it's fun.
Yeah, so you can tune into that and learn all kinds of Grasshopper trips. Highly recommend that. And I'm guessing Twitter's probably the best place for people to find that if they just look you up on Twitter. And then last, I want to say a really interesting thing Andrew's been doing is designing computational art. So I've seen actually quite a few people recently purchasing the art and getting signed copies of that. So if that's something that interests you, all that to say, Andrew's really kind of at the leading edge of computational design and definitely the right person to be telling us a little bit about data trees. So Andrew, as you get started, can you share with us just a little bit about what got you interested in computational design and your history behind Heumann UI and how it came about?
Yeah, totally. So I started out in a pretty traditional architecture program. I studied architecture in undergrad, and it was all sort of like hand drawing, hand drafting, and I nearly quit. I was so fed up with the tedious manual processes. And then one day I discovered Grasshopper thanks to a professor of mine, my mentor, Donna Kukova, who sort of introduced our class to Grasshopper. All of a sudden, there were all these things that you could automate, and it totally transformed the way I went through the rest of my schooling and totally ended up shaping my career. I really love Grasshopper both as a tool and as a creative outlet. And I really like the way that it facilitates kind of like the sharing of knowledge and ideas and processes and techniques in the realm of architecture. And I think that's part of where Human UI comes from. This was something where I was working at NBBJ in Seattle at the time, and I was building a lot of scripts, but it was hard to get other folks in the company to take advantage of them. Maybe they were intimidated by all the spaghetti. And so I had the idea of building a system to basically put user interfaces over the front of Grasshopper scripts and built Human UI. I was telling Tim earlier, I actually built the bulk of it on the beach in Mexico, or at least the beginnings of it.
I'm pretty sure that's what everyone does when they're on the beach. They're like, oh, you know what I'm going to do? I'm going to make a new user interface program app for the software that I'm really interested in. But no, that's really cool. Thanks for sharing. So what do you have for us today?
So today I'm going to be talking all about one of my very favorite topics, one which I think many people tend to think is a little bit dry and boring, and that's data trees. But it's something that I'm actually pretty passionate about. I think it's really the difference between a good user of Grasshopper and an expert user of Grasshopper is a level of mastery over trees, building a mental model of how trees work. And so I hope that with today's presentation, we'll add a little bit of clarity to your mental model as I share mine. Should I jump into the slides?
Go for it. Yeah.
Awesome. Okay.
Great. And while you're pulling that up, I will tell people that if you want to help get out information about these presentations, I've learned a lot about the YouTube algorithm. And actually, the best thing you can do is hit that like button. I feel cheesy just saying it, but as we really want to provide more to the community, that's one of the ways that if you think this is a good thing. So wait till you get to a point where you think Andrew has really crushed it, and then hit the like button. So go for it, Andrew.
All right. So I'm going to go pretty fast and furious through this. Tim has asked me to keep it around the realm of 20 minutes because I really want to leave time for questions. So I'm going to go pretty fast. But as we said, the recording is going to be available afterwards if you want to go back through the details, and there will be plenty of time to go back over anything in the question section. So as I said, I want to share my mental model of data trees. So what is the deal with data trees? What are they? They are the way that Grasshopper handles lists of lists. They're a record of the provenance of every single item. They're a vocabulary of operations you can use to transform the structure of the data, and a set of consistent rules for how components lace or match the data across multiple inputs to a component. So we're going to be talking about all of these components over the course of this presentation. So basics. In Grasshopper, data can be passed around from component to component in one of three forms: as a single item, a list, or a list of lists called a data tree. In a list, items have their own addresses called indices, which count from 0. So the fourth item is at index 3. In a data tree, each list, called a branch of the tree, has its own more complex address called a branch path. Grasshopper automatically constructs data trees for you. In fact, all data, even single items and lists, are just special cases of data trees. As I said at the beginning, they're a record of the provenance of every single item. To understand why this happens, you have to look closely at components. I'm going to introduce kind of my own made-up vocabulary for the kinds of components you encounter in Grasshopper so we can understand how they work with data trees. So a component that takes in single items and produces single items, like extrude curve here, is what I call a one-to-one component. You take in single items, you output single items on the other side. These components do not alter your data trees. So if you have a branch 0 on the in, you'll have a branch 0 on the out. And if you feed a component like this one a list comes out the other side. And the index of each output item matches the index of the input item it came from. So when I see index 1 on the output, I know that it corresponds to the index 1 on the input. A component like divide curve is what I call a one-to-many component. For every item you supply it, it will, or at least can, generate multiple items on the output. In order to keep your resulting data organized, these components append a new index to your branch path. So notice how the red numbers on the left are 0. We just got a branch path of 0. But on the right, it's 0, 0, because Grasshopper is going to tell us that this was a moment at which multiple things came from a single thing. And this is really useful when you deal with lists. So if I supply a list of curves on the input, it's going to produce new branches on the output organized by the item that generated them. So the index on the input, like the number 2, becomes the last index of the branch path on the output. So you can figure out which input item generated any tree by just looking at the branch indices. A component like polyline is what I call a many-to-one component. If you feed it a list in the input, it generates a single item on the output. It also does not transform your branch paths. In the olden days of Grasshopper, before there were data trees, if you wanted to construct multiple polylines, you had to make multiple copies of the polyline component. And I actually still see beginners do this all the time. With good mastery of data trees, you almost never need to copy paste groups of components.
Wait a minute.
Instead,
Are you
just
saying
structure your input
pasting?
into branches. Yeah.
Are you saying copying and pasting is not the best way to go about this?
It's not the best way to manage your groups of data, because what if you have to make a change to it? You now have to go back through and make changes to every single copy that you've made. Instead, if you organize your data into branches, then you'll just get organized data out the other side. You can basically have one component do many things for you by simply controlling its inputs. So how do we know? How do we know what kind of component we're dealing with? The answer is you hover over the inputs and outputs. You maybe have not looked super closely at this before. But if it doesn't say list or tree in the kind of yellow top portion of this, then you're dealing with what we call item access on either the input or the output. So if you have item access on both sides, that's a one-to-one component as I've described it. If you see as list on the left, you're dealing with a many-to-one component. You're dealing with a component that takes a list of data and produces items from it. So we know that will not transform our data structure. And if you get a one-to-many component with as list on the other side, you know that this takes in single items and generates multiple items on the output. So why does this matter? The reason why this is important is because of what I call the hierarchy of geometry. So in general, mastering Grasshopper is all about learning a new way of thinking about modeling. In this way of thinking, you're always building up complex forms from simple ones or deconstructing complex systems in order to operate on them in a more simple form. As you go down the hierarchy, you're often getting multiple items for every input item. So typically, as you go from more complex stuff to less complex stuff, you're dealing with one-to-many components. As you move back up, you're composing single items from multiple items. So usually you're dealing with many-to-one components. Let's walk through an example where we work our way down the hierarchy of geometry. So I'm starting with a list that has 2 polysurfaces or B-reps on it. What happens when I want to get the faces from those B-reps using a component like deconstruct B-rep, which takes in a single B-rep and generates a list of the faces? So that becomes a one-to-many component. When I feed it this list of 2 B-reps, it's going to organize the results by 2 new branches to tell me which B-rep each face came from. The faces in branch 0, 1 came from the B-rep at index 1 in the original list. Let's go one level deeper. What if we want to get all the edges of each face with a component like B-rep edges, another one-to-many component? Well, it's going to do the same thing again. It's going to create new branches, one for each face, with a list of edges in each one. And I know by looking at this branch path that the edges at branches 0, 1, 3 came from the face at index 3 on the B rep at index 1 in the original list. And that initial 0 is always the representation of the original list, the kind of root or trunk or base of this tree. So this is what this looks like in Grasshopper. You can see that we see in the panel this visualization of the little 0 in brackets, which is telling us the branch path. And we see on the left, we see the item indices with each of these B reps. And then as soon as I use deconstruct B rep, it's automatically created new branches for me, and it's labeled them with their branch paths. And as I go even deeper, it's appending new levels to this structure. So I also mentioned that data trees have a vocabulary of operations that you can use to transform the structure of your data. So let's look at a few of these and what they're called. So the most important data tree operation you need is graft. Graph does the same thing that a one-to-many component does automatically. It puts every item on its own list. So every item is moved to its own list, and what was previously its item index gets appended to the branch path. Now every item is at index 0 in its own list.
Those animations are awesome, by the way. Just have to compliment, though. I know those must have taken hours to create, but it's really helpful for understanding how this all works.
I went a little keynote crazy, and believe me, we're not done yet. The opposite of a graft is, I think, the second most important data tree operation. You can think of it as sort of like an ungraft. And this has two names in Grasshopper for reasons I do not understand. There are two components that basically do the exact same thing. One is called shift paths, which is the one that I use out of habit, but it's basically the same as trim tree. So what does this operation do? It takes a tree and it effectively chops off the last index of each branch path. So items that were previously on separate branches are grouped back together based on their new truncated paths. So items in branches that started with 0, 1, like 0, 1, 0, 0, 1, 1, 0, 1, 2, are now all back together in branch 0, 1. The last operation I'm going to talk about is also the most destructive. So if you want to discard your tree information entirely and condense the whole tree into a single list, you can flatten it. This is equivalent to doing trim tree or shift paths for as many levels as are in your branches. So you can basically get this all the way back to the root. Now, the reason why I say this is destructive is because what you've effectively done is totally blown away all of the tree information that was embedded in your data, and now you don't know where any of this data came from. And sometimes you need that information later on. We'll see some examples of why this is challenging a little bit later. So in order to really work with data trees, you need this mental model of how items from different inputs are matched to each other. And this is what we call lacing or data matching. So if I have a component that does something with some data going into input A and some other data going into input B, how do I know which pieces from A and which pieces from B it's going to do that thing to? How many times is it going to run? How is it going to match these things together? So I'm going to explain this in the context of components that have item access, that are sort of one-to-one components. But most of these rules apply generally, and this will help you build a general intuition for how this matching works, because it's basically the same thing over and over and over again. Let's take a concatenate component, which just joins two pieces of text or two things together. And we're going to give it a list of length n. And I'm going to use these like variables for the list length. So n is the length of the items in the list. This is an n equals 3 list here at the top, and an n equals 1 list at the bottom. So I'm matching a list of length n to a list of length 1. And I want to concatenate these two lists together. And what it's going to do is just match the item from the single list to all of the items in the list of length n. So we get A and 1 together, B and 1 together, and C and 1 together. Now, if you have two lists of length n, then it's going to do something slightly different, which is it's going to match these items up by their index. So the item at index 0 in the first list is going to match to the item at index 0 in the second list. So A goes together with 1, B goes together with 2, And C goes together with 3 because those things matched in their input indices. So hopefully for many of you, this is review. This is like pretty obvious and pretty simple. And even if this is new to you, hopefully these concepts feel pretty simple. But where it gets scary is when you start dealing with branch matching behavior. But the good news is, if you understand this, you already understand branch matching behavior. And this is because branches get matched exactly the same way as items. It just happens twice. First, it matches the branches into pairs, applying the same logic where you have either M to 1 or M to M. And then for every pair that it creates, it's going to match the items according to the same logic again. So N to 1 or N to N. So let's walk through a few examples of how this works. So in this scenario, we have 2 branches in the A input and 1 branch in B. And the branches in A each have 3 items, and the branch in B also has 3 items. So first, we're going to match the branches, and we've got M equals 2. I've got 2 branches on the input, and M equals 1 at the bottom. I've got 1 branch. So it's going to match the first branch to that branch, and then it's going to match the second branch to that branch. And it's made these pairs. And then it's going to apply item level matching. So just like we saw before, it's going to match 0 to 0, 1 to 1, 2 to 2. So we see 0 to 0, 1 to 1, 2 to 2, and then it does it for the second branch, 0 to 0, 1 to 1, 2 to 2. Okay, simple enough. It's matching by branches, and then it's matching by items. Let's do another one of these. This time, we'll use a structure where we have, let's see, is this the same as the previous? Oh, here we go. Yes. So now I have 2 branches on the A and 2 branches on the B, but the second list branches only have 1 item apiece. So this time it's going to match branch 0, 0 to branch 0, 0, branch 0, 1 to branch 0, 1. And then it's going to apply item matching. And since this is an N to 1, it's going to go A1, B1, and C1. And then in the second list, I bet you can guess, we get X7, Y7, and Z7. So if we have an even more complex structure where these things actually match up completely, it's actually fairly obvious. Every item ultimately gets matched, but it follows the same logic. We have branch to branch, and then in those pairs, it does item matching. So we're going to do 0 to 0, B to 2, or 1 to 1, 2 to 2, X7, Y8, Z9, because it's matching those things by their indices. So now I'm going to give you a fairly opinionated set of rules for how you maintain healthy and happy data trees. And these are intuitions that I've built up over 10 years of working with Grasshopper. However, that doesn't mean that they are inviolable. It doesn't mean that everybody agrees with me. There are lots of people who are really good at Grasshopper who fundamentally disagree with me on a lot of this stuff. So just know that this isn't like gospel. This is one person's opinion. But I have found that if I follow these rules, I get some really significant benefits. So that this idea of like a healthy and happy tree, what I mean by that is trees that work in a predictable way that allow your scripts to be robust to changing input. So your scripts will be able to tolerate inputs that change their shape, that change their count, that change their tree structure, and the script will still work. And that's really important when you want to make reusable scripts, say in clusters, because you want to make some logic that will work in any circumstance. So you have to follow rules like this to make sure that your scripts inside your clusters don't break when somebody throws a different tree structure in. So the first rule is all paired branches should either have n items or 1 item. So each set of lists that talk to each other should have n, where in this case, n equals 4. So I can have 4 items against 1 item, and it's going to match that 1 to every 4. Or I can have 4 items and 4 items, and it's going to go 1, 2, 3, 4, and match them all up along the way. You almost never want the case where the 2 lists have different lengths. It will work. Grasshopper knows what to do when you put 4 items on this side and 2 items on this side. What it does is it just repeats the last item. This is what's called longest list matching, but it's almost never intentional. It's almost never the thing you want, but it's a frequent mistake I see beginners make. in almost no case is it actually necessary to have two sets of inputs have lists of different lengths. This same rule applies to branches. So if you have 20 branches on one side, you can match it up to one branch on the other side or to 20 other branches. But I wouldn't match 20 branches to 5 branches. If you need to get these two branches to talk to each other, you need to use some of the data manipulation operations I've showed earlier, as well as maybe some more advanced ones, which maybe we'll get a chance to show a little bit later. You have to make the branches on the right agree with the branches on the left. So there are ways to do this with grafting longest list or propagate ancestors from tree sloth. And maybe I show this a little bit at the end if we have extra time. If you see the thing on the right where there are branches that have different branch path lengths, something has gone wrong. This is what we call like a code smell in Grasshopper. This means something is bad. Somewhere your data is not rectangular and aligned. And so this is a bad sign. You always want what I refer to as rectangular trees, where it doesn't mean that all the branches have to be the same length, but it means that all of the branch paths need to have the same number of indices.
And can I just point out what I think you're saying? I think what you're saying is not that there's 2 items, 1 item, but that there's one branch, one I don't know what you call that, but
one branch index.
One index level branch and then 2 index level branches. Is that what you're pointing out here? Perfect.
Yes, exactly. So it's the headings, it's not the items. It is totally okay to have branches of different lengths where I have 2 items in one and 1 item in another. It is generally a bad idea to have branches that themselves have different numbers of indices. It's usually a sign that something has gone wrong. Okay, on to the meaty part, the part you've all been waiting for. Why do I hate flatten so much? So the reason I hate flatten is because it is an absolute operation and it just discards all the data, like I said before. But perhaps more importantly, it prevents you from ever reusing this code in a flexible way. So these 2 scripts are identical at the moment. I've got one with flatten and one that uses trim trees, and they work great when I have one surface on the input. But as soon as I feed multiple surfaces into the input, you can see I've just changed that out. The one at the top, which uses trim tree, gives me 2 polylines back. So this routine is a way of generating a polyline from a surface. If I feed it 2 surfaces, I want 2 polylines out. I want my clusters and my groups of components to behave like components and that they sort of respect the data that goes in. With flatten, now I've got a single polyline from my 2 surfaces, which is probably illogical. If that was intentional, then I could just trim the tree a couple levels deeper. And then, in a scenario where I've got 2 groups of 2 surfaces, I would get the right thing. The next one that I rant and rave about is simplify. The reason I hate simplify is because it results in trees that can change shape based on the changes in input, which can break things. So here's an example, and I'll actually show this one live, I think, here in a second. So these routines are identical. You get a loft out of this sort of input here. But it works when I have multiple things going in, but as soon as I have a single thing, it breaks. This merge has broken because you can see I've got, I can't use my pointer when this is in full screen, but this panel over here in the lower right has one item with 0, 0, 0 and one item with 0, 0, 0, 0. So those 2 things don't merge, my lofts fail. The previous one, the simplify, was handling, making sure that those were of the same length, and so they would merge together. If instead I insert a shift paths upstream, so I've removed the simplify and just shifting the paths to force my trees to be the same length so that I can merge them, then this loft works when I have multiple items. And it also works when I have a single item because the trees have not changed on the basis of the data input. So let's actually look at this one in Grasshopper. And that's actually my last official slide. So I'll jump into this example and then we can move on to questions. How did I do on time, by the way? Was that about
you're doing
minutes?
Great. Yeah, you're doing great on time.
Okay, awesome.
Now the rest of it will depend on what kind of questions we get,
Well, yeah. So I'm gonna be put on the spot. I can tell. Okay, so here's this sort of like funny contrived example that I built, where I've got a pipeline, a geometry pipeline that's referencing in geometry from Rhino. And this is a common case where, you want to build a tool that uses some stuff from Rhino. And so I'm creating this sort of interpolated curve on the one hand, and then I'm creating these like differently located circles on the other hand. And I'm even using the list length of the input so that I get the right number of circles. So if I add another one of these rectangles, I should get a new circle. I have to be on the right layer. Let's try this. So if I add another rectangle, it adds another circle. Everything's hunky-dory until the moment at which I only have a single rectangle. Now, over here, we've got mismatched branches. This is that bad smell scenario that I was talking about earlier. And the reason this is bad is because when I've merged these things together, Loft is no longer operating on these two things that are meant to be in the same list. It has to operate on them separately. So how do we solve this? Let's actually just directly modify this. The first thing is kill all simplify. And then what am I left with? So I can see that there's still this mismatch here where this one has 0, 0, 0, and this one has 0, 0, 0, 0.
So you know at this point you've done two operations that split them, and so you're seeing here that you've got this like difference in your data structure.
Right, exactly. This is one operation. This is another operation. They've resulted in a mismatch of the levels. I'm going to do this. I typically do tree debugging in the worst case scenario where I have like the most complex imaginable tree, which in this case is just multiple items on the input. So I can see that, and this was the problem I was probably solving with that simplify in the first place, was that these go 0, 0, 0, 0, or 0, 0, 0, 0, 0, 0, 0, 1. These go 0, 0, 1. So there's an extra 0 up front of the moment that I grafted somewhere over here. So all I need to do is, and it's useful when debugging to sort of use a panel to inspect. So at this moment, we were at 0, 0. This moment, we're at 0, 0. At this moment, we're at 0, 0, 0. And at this final moment when I've grafted, we're at this sort of the final place. So if I do a trim tree here, I'm going to have a problem because this last index is the one containing all of the distinction information that I need. If I shift pads here, we're just going to get a flat tree because these are all belonging to 0, 0, 0. So I actually have to insert this shift pads upstream. I can just do it right here. And if I do that, then this is now outputting 0, 0, 0, 0, 0, 1, 0, 0, 2 in a way that aligns with the one coming out of here. And now my merge is happy. And now even if I had a single item, this would work fine. So I think I have a few other examples of that, but I think it would probably be best to just move straight into questions because I kind of like live working through these problems based on questions.
No, that's great.
I'll stop sharing my screen.
We definitely encourage you to bring the questions up as people are thinking through their questions. I have one that kind of relates to what you just said, just to kind of re-talk over it. So you're saying like, look, we're not going to be trying to remap our paths at the end, saying like, oh no, the fourth one is actually the third one, but go to that extra spot that split it that didn't happen in the other, I'm going to call it like river of flow, and then just remap that tree where you did.
Yeah, and so I think actually you bring up a really good point, which I neglected to mention, which is that like basically every time you get one of those zeros, those extra zeros in your path, it's because of an operation that could have produced a list but didn't. So let's investigate that in the context of this script. So which operations are adding this 0? So we start with our root over here. And actually, I think because dynamic pipeline takes in single items and generates a list, we're already getting this 0, 0. So we're starting from there. When we get to flip, that shouldn't do anything because this is item. But at this moment, I can kind of pull it back to a 0. Series can generate multiple items. And in fact, we normally would want it to. But in this particular case, we only have one item we're trying to match it up to. This is what's generating those circles. And so it's okay that it only has one item. And then we wind up over here with this 0, 0, 0. So what I'm getting at is that basically you want to do the P shift at the moment that something has produced more than one index than you needed, but you know that there's no scenario in which it could. Mm-hmm. So you basically want to like, I think people are attracted to simplify because it makes the tree really understandable. It's like,
you're like, I just made this 5-piece into one, and now I know that it's one over here, and I know it's one over here, and I can work with it, and it just like magically does the not flattening, but like organized flattening.
Yeah. So yeah, exactly. So I think that like you just want to like, rather than you have to resist the impulse to get like 352 from 30 or 0300050002. You still want to clean up those trees, but you want to do it deliberately at the moment where they occur. And then you'll actually have a lot less simplifying to do downstream anyway. You just find it the moment it arises and then just trim it out. And that's an explicit assertion that like, even though this thing can produce a list, I know in my particular use case, it's only producing a single item, so I can safely remove it. It's a much more sort of intentional approach.
So I'm going to move on to some of our questions because we have some really good questions coming in. And I do want to start with the last one that came in. And that is, so what you're presenting is not the gospel of data management. What's the alternative perspective? And I almost want to push it back to the chat. There's like at least 40 people watching this live right now. And I know we're going to get, like 400 people who are going to watch it afterwards. So let's see those comments and the questions. Let's see what other people think. And Andrew, why don't you answer it while we're at it too?
Yeah, I mean, that's like a really good question. I don't know that I have a great answer. I just know that there are a lot of like people who are very savvy, accomplished Grasshopper users who like disagree with me on this and are always surprised to hear me say it. I think there are other ways, and actually I saw another question about this come up in the chat. There are other ways to kind of protect yourself against the evils of simplify. One is to use third-party versions of shift paths like shift paths safely, Nick brought up in the chat, which will basically, it's exactly like shift paths, except the problem with shift paths is, let me just quickly show my screen. So if you shift paths on a list that is 0, then it breaks. It was shifted out of existence. Shift paths safely basically just protects you from bottoming out, protects you from the case where you try and shift paths on a single branch index. So that's all shift paths safely do. And I think there are sort of like various tools that people use to combat the dangers of simplify. I think another one that I've seen a lot, there's a fellow on the Grasshopper forum named Olivier Swire, I think, who forced David to introduce a component called Swirify, which is effectively a simplify that also sort of like avoids bottoming out or avoids some, I forget exactly how it works, but it's meant to be like a safer simplify. So you may find
and it's called
that this is better. Swirify.
Swirify. Like safely simplify or something?
Name.
Oh, okay.
Yeah.
Gotcha.
His Olivier Swire, I think is his name.
Gotcha.
And I may be pronouncing that wrong. Mm-hmm. In any case, there are sort of like crutches that people use to avoid actually like deliberately managing the trees. But the ultimate problem, and the reason why I resist them, is that it's still no matter what, it can still change shape based on the inputs that you supply. Let me see if I have this other example open.
As you're thinking about that, I do want to bring attention to this question about where can I go to try some of these things out? Any ideas on practicing some of these? And I want to add to that question. Can you give me an example where I know things are going to break and you will have proven your point for us to experiment with, us being the chat?
Sorry, can you say that again?
The question is, where can I go to practice these things? And I'm kind of adding to that question of where can I go in such a way that it will break unless I follow your rules?
Yeah, I mean, I think.
And the example said that
yeah,
the person asking the question said that they've tried using trust structures, but they want to go to the next level of complexity.
Yeah, I mean, I think that this stuff starts to emerge at the moment you start going back up that hierarchy of geometry. So examples where you're taking stuff and breaking it down, typically Grasshopper's automatic data management does all the work for you. You don't have to worry. Where things get complicated are when you break stuff down and then have to rebuild it, because maybe one piece you pass through this routine and this other piece you pass through this other routine and they come out mismatched. So I think it's in the moments where you're kind of like constructing new geometry from whole cloth, or from something that you decomposed earlier. So you can try an exercise of like, okay, let's take a box and then let's decompose it into its faces, and then let's decompose those faces into their curves, and let's decompose those curves into their points, and then let's do something with the points. Let's like manipulate them or transform them or scale them or move them based on an attractor, and then let's use that to rebuild a new set of geometry, all the way back up to the box if you can. So, I think those are the
kind of like working
scenarios
all the
where
way
this stuff
down
emerges.
into separating things up and then rebuilding it. So,
And rebuilding all
and
the
there
way
may
back.
be like a real
Right.
life example, or it could just be, a practice problem to like really understand.
Yeah. I was trying to look for some like real examples from past work. And unfortunately, like all of my professional Grasshopper scripts are like buried in an external hard drive somewhere. And so all I have are my like super messy like art scripts where I still use this stuff, but I would be ashamed to show you the spaghetti that I keep in my personal stuff.
Yeah, you didn't mention anything about the Pathmapper. Can you talk about some of your personal experience with that?
So the Pathmapper is another one of these things that I don't like, and I don't like to use because it's dependent on your data being in a particular structure. So, if I have this data here and I use the Pathmapper to say, okay, I'm going to take 0, 0A, and I'm going to turn it into 0A, 0, let's say. And then something changes upstream, like something I didn't expect. Maybe I got like, I'm just gonna fake this real quick. Let's see if this does anything. And we'll say we'll graph this. So something has changed about my data structure. Oh, I guess that was a bad one. Let's try here. If we graph this, it should do it. So something has changed upstream, and now this is no longer following the pattern that this was matching for. So it's broken. It no longer does the thing that I need it to do. Instead, I always use relative operations measured from basically like the rightmost end of the path, because upstream changes will only ever affect the left end of the path. So always do your operations by like popping one thing off the end or popping two things off the end, rather than trying to make massive changes over at the front, because that's where you get.
Because later, if you want to change something higher up in your stream, it's going to mess up this Pathmapper operation that you've created.
Yeah, exactly.
No, that's great. Can you explain the relative items component?
I can try.
Pretty general
It's not
question.
one that I use.
You also mentioned another one that I haven't heard of. I'm guessing it's inside of somebody's custom package, but I can't remember. If I think of it, I'll bring it up.
Yeah. Oh, I think it was the shift path safely, maybe.
Yeah, there was another one
in the chat. Oh, there was another one. Okay.
Yeah.
In any case, so relative item 2 allows you to take like two data structures. Let's see if we can actually like use this real quick. This may be a fool's errand because this is not a component that I often use. But let's just say we want to take all of these, we want to move them up by some list of vectors, and we want to divide each one of these. And let's just make this a little taller. So, okay, so I've got now a tree where I've got all of these items. And what I want to do is I want to like match this item to this item and this item to this item. I think this is what relative paths or relative items allows you to do. You can basically like pass it. And in this case, I'm just going to pass it the same thing. And I can set an offset for either the branches or the items. So let's say if I do, let's try, and I haven't used this in a while. Let's do 0, 0, 0, and 1, I think is what I want. Let's try this. What does it expect? Offset mask is not valid. I forget how these masks are composed.
So it's kind of like shift item in a tree, but you can also do it for a branch. Is that kind of what you're showing?
Yeah, it's exactly like that. And it allows you, there we go. So now if I were to draw a line between these two things, it's going to connect within the list because my shift is only within the list. I've only done a shift at the list index, not at the branch indices. But if I also insert like a shift here, then I can do things like a sort of diagonal patterning where it's going to basically connect from an item here and it's going to shift the paths by 1 and then shift the item by 1 in order to get me to this kind of diagonal thing. So you can do some patterning with this. Again, it's not something I like use very much, but I believe that's what it's for.
That looks really powerful. I've actually never used it either as well. I end up restructuring it so that I can just use a shift. But we have a couple of good questions here. Other questions. Same. All questions are good, but a couple other good ones here. Where was I? I was on... Oh, what's the difference between merge and entwine?
Okay, good one. So merge basically is just the same as holding down shift when you put stuff together. So if I have some data structure here and I hold down, and this is going to be, well, here, let's do it like this. I have my A's and I hold down shift and I have my B's. That's the same thing as merge. It basically doesn't transform the data trees at all. It just layers them together. And it'll do so in kind of an item order. So it's going to do the first one I plugged in is the first 9 and the second one I plugged in is the second 9 in this list. So I wind up with 18. So this is equivalent to using merge. And the reason why I like merge rather than holding down shift is that you know what order these things were plugged in. If you just use shift, you don't really know whether I plugged in this wire first or this wire first, which actually does affect the order of the data that comes out. So that's what merge is for. Entwine, on the other hand, basically has a sort of built-in flatten operation. That's why it says flatten here at the bottom. And what it does is it basically like pre-constructs some trees for you and allows you to just feed items directly in. And it will wipe out any tree information on the in. And then if I do, let's put a couple sliders in here, it's going to put the things in their respective branches. Now, this is in itself, even though this says flatten, this is often a really useful way. If I've got like, let's say I've got now, these 3 curves, I'm going to graft them so that they also have 3 branches. And I'm going to extrude those curves by these distances. And what that will do, like this is a really good way to put manual input in a way that's structured in a tree that you expect. So this has done, this one affects the first curve. These 2 affect the second curve. You can see it's kind of overlapping itself. Yeah. And then this one affects the third curve. Now, the one other cool thing about flatten, and actually this I like quite a lot.
So this is an Andrew approved flatten. Is that what you're saying?
Yes, yes, it is. As long as you know what you're doing, and in general, like as long as you know what you're doing, flatten is fine. But you only should use it in a scenario where
you really want a flat structure because you're planning on doing something. Yeah, we do have a couple other questions I want to get to. So we've got about 3 or 4 more minutes. We're going to keep this live before we cut it off. So if you have any final questions, throw those in there. So I wanted to get to how do you maintain the tree structure in context of script node in Grasshopper, such as Python or C#?
So this is a great question. I see a lot of people immediately think that they need to go to tree access on all of their scripts, and then they have to wrestle with these complex structures in their code. You almost never want to write a script or a custom component that takes tree access unless you absolutely know that you need access to the whole tree at once. This is actually, I think, even for non-scripters, I think this is a useful thing to point out. So when I right-click this input and it has these 3 options, those are the things I was talking about. I only talked about item access and list access because they're by far the most common you'll see in any component. There's also this mode of tree access. And what this dictates is like, how many times does the code run? So I'm going to feed it this data tree, let's say. If I leave it at item access, which is what I do 90% of the time, then all I have to do, and the max scripting component kind of sucks. Normally you can actually like see the signature of the function. You can see what you're doing. But effectively, this value X, since I have item access, is just a number. So I could do things like A equals X times 4. And it'll force me to set this to be a number before it'll let me do that, which is a double. And then now I will have gotten those numbers multiplied by 4. So sometimes you actually need access to the whole list, but it increases the complexity. If you right click and choose list access, I can no longer say X times 4 because X is not an item anymore. It's a list, and I have to write a for loop. So just compare that code to this, which is like, var my list out equals new list of double, and then we'll say for in I equals 0. I is
because now you're having to handle the list,
et cetera, et cetera.
You're having to handle the list instead of Grasshopper handling the list. And
right, yeah, exactly. So all of a sudden it's way more complicated. I can get the items in X, but it is really, you should always use the lowest tree structure you can get away with when you're developing custom scripts or components. And I believe Python has the same control.
Yeah, it does.
Yeah,
definitely.
Yep.
All right, let's see here. I just got another question that came in. Let me make sure I go back through and hit all the other ones. By the way, thank you so much. It's been great. I know I'm going to hit that like button when I get a chance to. And let's see here. So aside from clustering, is there a way through data management to duplicate the same operation, even if the data structure varies?
So
if I understand the question right, I think they're asking like, can you copy the scripting without clustering? Is that right? The question I'm understanding?
I would say, if in general, I don't recommend using a single object to process like data of different structures at the same time. So this is the moment where like you might have to copy paste because you've got like two totally separate things, and even though they're using the same operation, you can, you want to run them separately. So that is a case where I will cluster. I actually think clustering is a really useful technique for that, where I have some logic that I want to repeat in multiple places against different input structures. And the beauty of using these data tree rules is that you can do that safely. You can do it knowing that it will handle the variable structures and do the right thing without, ruining your tree.
Mm-hmm. So the biggest clue I really picked up today is P shift or trim, because they're the same. Yeah. At the earliest possible point where that's where you want it to happen. Is that a fair?
Yep.
A fair statement?
Yep, so. Absolutely. If you take one thing away from today, I think that's probably the best max.
And avoid simplifying and flattening all over.
Yeah.
So with that, I'm going to say thank you, Andrew, so much for your time. Go ahead, say thanks to him in the chat. We really appreciated it, and we will see the rest of you in 5 days, I guess.
Yeah, thank you so much for putting this on. This series is awesome, and I'm really honored to be a part of it.
Great. Thanks, Andrew. Bye, everyone.
All right, thanks. Bye.